Please respond whether you have joined, all of you.
Yes, sir.
So should I start the class? So is the screen, entire screen is visible to all of you? Systems and microprocessors. So there are two parts. The part one is sequential systems. The part two is microprocessor. So 4 teachers will be taking, or no, 2 teachers will be taking for your sections, section A. So it's a Shantan Chakraborty and me, Palash Kumar Kundu. So we start with the subjects. You require the knowledge of digital electronics. Perhaps you are familiar with the basic digital logic, that is Boolean logic and the Boolean function, and the digital electronics. That means in digital electronics, you must be conversant with the combination logic, that is logic gates, using a combination logic circuit using logic gates, and sequential logic circuit. Perhaps the sequential logic circuit has not started. So the digital electronics domain consists of these two building functional logics, that is combination logics and the sequential logics, which are built with integrated circuits, ICs. Now, the microprocessors is an application of the digital electronics, application of the digital electronics in a sense that means it is a first origin of the computer, That means utilizing VLSI technology, very large scale integration technology, the microprocessor can be built by the manufacturer. Now, you must have some brief idea, or you must know the history of microprocessor. That means what is meant by a microprocessor and what are the building blocks inside a microprocessor, or what is called the any typical microprocessor. What are the specifications of the microprocessors? Now, the origin of the microprocessor started in 1968 when the 3 technologists, Robert Noyce, Gordon Moore, and Andrew Groove, have designed a Fairchild Semiconductors Incorporation, USA, the leading integrated circuit manufacturer for manufacturing the digital logic gates. And they have formed a company called the Intel. The abbreviation is Integrated Electronics. So in 1968, this is the roadmap has started. But the Fairchild Semiconductor has, which was founded in 1957, invented the first kind of the ICs using the VLSI technology in 1959. But in 1968, the first microprocessor, that is 4-bit microprocessor, what stands for bit. You know, in logic, in binary arithmetic, that means the binary arithmetic is which consists of the 2 symbols, 0 or 1, high or low. Any number can be represented in terms of the binary number consisting of the finite number of the bits, like 4-bit, 8-bit, 16-bit, and so on. So the unit of the binary number is a bit. The value of the bit may be low or high, that is 0 and 1. So 4-bit means the number can be represented by a 4-bit number. What is the formula? It is 2 to the power n, where n is the number of bit minus 1. So in 4-bit microprocessor, the microprocessor could handle the maximum binary number. The decimal equivalent is 15. Why? Because 2 to the power 4 minus 1 is 15, including 0 value. So there are 16 integer in binary arithmetic. So the first microprocessor can perform the mathematical operations Now, what is mathematical operation? That is the arithmetic operation as well as the logical operation. Again, you must understand what is the arithmetic operation, which is nothing but a summation, subtraction, multiplication, or division. And what is logical operations? That means AND logic, OR logic, XOR logic, NOT logic, etc. and so on, which are the fundamental logic operations. So the microprocessor, that is the first kind of the microprocessor, which is 4-bit microprocessor in 1968, could perform the arithmetic logical operations. Maximum value of that number is 4-bit. The decimal equivalent is 15. So first kind of the microprocessor, 4-bit microprocessor, the model name is 4004 in 1971, introduced by this Intel. It was a 4-bit microprocessor. Every microprocessor internally is its internal architecture consists of a huge, large combination as well as a sequential logic circuit. So for the basic idea is for operations of the sequential logic circuit, a clock and the timing signals is required. But for combination logic circuit, no timing and the clock signals is required. That's why in case of a AND and the or inversion operation, the bitwise only a input in the form of binary bits is required. So that's why as the microprocessor can perform in respect of the time slots, so fundamental or the basic primary signal, that is the timing signal, is required. And Intel 4004 microprocessor utilized the 740 kilohertz timing signal. That is the time period of the one clock period is 1/740 kilohertz. And it was built with a 2300 transistors using VLSI technology, would execute around 60,000 instructions per second. That is another implications of the microprocessor. That is, it can process the arithmetic logical operation in microsecond time. So as the name implies, that is why the device is named as microprocessor. It could execute around 60,000 instructions per second. So fast is that means operation. Per unit second, it can execute the 60,000 instruction. The instruction means it can perform the arithmetic as well as the logical operation instruction and machine control instruction other than arithmetic and the logical operations. So that is the fundamental idea of any microprocessor. First of all, the specification, the major specification is the data width in the form of bit, like 4-bit, 8-bit, and what is the clock rate and the clock speed. For example, 740 kilohertz is the clock rate. These are the two fundamental input specification for a microprocessor for analyzing its performance, how fast it can perform the operations. The next kind of the microprocessor is the Intel 4040, which is a modified version of the 4004. In 1974, it has the data width is about 4-bit. Microprocessor has been formed. The part name is 8008 in 1972. The clock speed has been increased to 500 kilohertz. It could execute 50,000 instructions per second manufactured by Intel. Then 8080 comes into the picture. In the same year, 1974, it was a 8-bit microprocessor. The clock speed again has been raised to 2 megahertz. That is 2000 kilohertz. 2 megahertz means 2 into 10 to the power 6 hertz. So the clock speed is quite high. It can execute, that means large number of instructions per unit time, that is second. 5 lakhs, so high, which is 10 times faster than 8008. Then the first kind of, historically, the first kind of the microprocessor, 8-bit microprocessor, is the 8085, introduced in the year of 1976. The clock speed, it can execute 7 lakh 9,000 instruction. And one of the another major specification of the microprocessor, that means these devices, which is IC chips, microprocessor IC chips, internally includes some storage element called registers. So finite amount of the registers it has, other than memory or the semiconductor storage elements. The memory and the semiconductor storage elements should be interfaced, connected via its external pin, that is the through which the input output signal are associated, can be connected. So 8085 can access 64 kilobytes of memory. Kilobytes means what is the volume of the memory. It can handle, it can perform the arithmetic logical operations with the help of 246 types of the instruction. The instruction has been designed by the manufacturer Intel Corporation. So this is the first kind of the 8-bit microprocessor historically. Then the 16-bit microprocessor has evolved in 1978. The data width is 16 in number. Clock speed is still higher, very much higher, 4.77 megahertz, 8 megahertz, and the 10 megahertz versions are available. The data width is 16-bit, and it can access 1 megabyte memory block. Using the 20-bit address signals lines, it can access 1 megabyte of memory storage. It has an instruction like 22,000 instruction, which is written in the machine language or binary language. So this is the first kind of the 16-bit microprocessor, Intel 8086. Then 8088 is still, it has a dual mode operation. It can be used as an 8-bit operations, 8-bit data as well as 16-bit data access. So basically it is a subset of the 8086. 80186, 80188 microprocessor comes into play in 1982, which has a higher data bus like 16-bit, 24-bit, etc. It is available in the square pack IC. But before that, it was the ICs were available in the dual inline package or the DIP package. So still the 80286, another microprocessor which was utilized in the personal computer in 1986 or PCs. So the first kind of the PCs used Intel 80286, which is a 24-bit or 32-bit microprocessor. Then the two 32-bit microprocessors have been entered into the market, that means 80386. It is called the 32-bit, the data width is 32. It can access 4 gigabyte of memory, very high. So semiconductor memory volume is 4 gigabyte. Before exceeding with the 4 gigabyte, it cannot access any other memory locations. Then 80486 is also a 32-bit, and it has a many input features. 1.2 million transistor, utilizing 1.2 million transistor. The clock rate is very, very high, 16 megahertz to 100 megahertz. So 100 megahertz clock circuit it has, so high. It was used in the Pentium processor, 80486. So in 1993, Intel Pentium processor have evolved, which is a 80586 processors. The clock speed is 66 megahertz. Then Intel Pentium Pro, or called the Pro processors, introduced in 1995. It is a 32-bit microprocessor. Then Intel Pentium 2 in 1997. It can be used as a 32-bit as well as a 64-bit, which is very common. And Pentium 2, Exxon, and so many models, and still it is going on. Right now, the standard PC in laptop or the computer uses so many model standard. The name is not Pentium, but other things, dual core, quad core, etc. So these are the application history of the microprocessor inside the IT machine, that is computer, as well as a real-time microcontroller or microcomputer-based systems for automation, automated product. Anyway, this gives a brief idea about the history of microprocessors and some model. Now, we must have some idea the basic internal architecture of a typical 8-bit microprocessor, that is the internal architecture of 8085. Inside the 8085, what are the building blocks? First of all, internal architecture of the 8-bit microprocessor consists of this building block: registers, arithmetic logic unit of ALU, instruction decoder, machine cycle encoder, address buffer, which is a particular type of registers also, address data buffer. Again, it is register. Mean it will be clear in the sequential logic circuit, that is the input binary number is stored, buffered inside the semiconductor element, or that is storage locations. Basically, it is a sequential logic circuit, the register is. Then incrementer, decrementer, address latch, till these are the special type of registers. Interrupt control unit, which is a big sequential logic circuit. Serial data IO control unit, a large sequential logic circuit, and the timing and the control logic circuit. So these are the fundamental functional block or the building block at the internal architecture of a typical 8-bit microprocessor. Here it is 8085. So this is a pictorial functional diagram called the architecture of 8085. Now, I have shown the legs and the pins connecting the external world. The pins is made with a either gold coated or very conductive material coated electrodes or terminals. So these are the functional name of the terminals or legs or pins associated with it. And these symbols is nothing but a particular group of the electrical parallel wires called the bus. So here a single line indicates the particular signal, but this is called the group of the electrical signals which runs away parallelly in the internal block and called the bus. For example, address data bus. Now, how much is the total number of the signals associated with a bus? According to the nomenclature, the particular signal names is called AD0 to AD7, means there are 8 number of the signal lines parallelly run away. The signals are nomenclatured by AD0, address data least significant bit, to address data most significant bit, AD7. So this is another bus named as A8 to A15. That means here also the 8 signal lines are coming out. The bus is associated or indicated with its direction. It is a bidirectional address data bus. That means the signals may flow from external world to inside, or signal may flow from the internal to the external world. So that's why there is a bidirectional line. But address bus is an unidirectional. That means the signals can flow from inside or internal architecture to the external world. The other bus, or internal bus, is bidirectional, must be bidirectional, which access the signal from its internal registers block called the general purpose register, the GP register. The particular name is W register, Z register, B register, C register, D register. Each register internally has 8-bit width. So the 2 registers may form the 16-bit, but the internal bus length or the size is 8-bit only. So that's why it is called the 8-bit internal data bus. The name is called data bus. That means data can flow from the external world to internal any one of this registered unit via this internal bus. So this is a very important functional unit called the arithmetic logic unit. That means whenever some arithmetic operations is performed by the 8085 microprocessor, internally it will go to this block via the internal data bus. Another group of signals which are called the timing and the control signals, which are coming in or coming out or both from this timing and the control unit. But it is a large sequential logic circuit. In fact, it is the heart of the microprocessor, from which the different timing and the control signals are associated, which have some specific directions. Some of the signals are unidirectional, either from going out, and some of the signals are going into this block. So any sequential logic circuit requires the fundamental timing unit or timing signal that is coming from the clock signals. So x1, x2 are the two lines through which the 50% duty cycle square waves called the clock signals is applied to the timing and the control unit. So in respect of the different time slots, each and every operations will perform. Means each and every arithmetic and the logical operations will be performed, will take place. So this is in brief the internal architecture and its description. So these are described here in the following manner. So it has an 8085 has an 8 addressable 8-bit registers called A, B, C, D, E, H, L, F, and the two 16-bit registers called program counter PC and the stack pointer SP. These two things. So these are the register, but it is a 16-bit. These are 16-bit register, except these are 8-bit register individually, but can be operated as a 16-bit, 2-bit, 8-bit pair, fixed pair. The pair name is fixed, so that means it is not random. Like BC pair can be operated, DE pair and the HL pair. Other than 16-bit registers or the two 8-bit pair like BC, DE, and the HL, they can also be used individually as an 8-bit register like B, C, D, E, HL. So 6 registers are there. These are called the general purpose registers or GP registers. WZ are called the temporary register. That means whenever the arithmetic logic operations are performed, temporarily it will be stored either W or Z or both. So that's why W and the Z are called the temporary registers. So special purpose registers, among the special purpose registers, accumulator, flag registers, instruction registers are the main things. So this is the accumulator. This is the accumulator, the special register, because arithmetic logic unit is not a register, but some sequential logic circuit, which takes the two input, that is two operands. For example, for summing, only the two operands A and B will be required, or X and Y. But for complementation or not, only the single operand is required. The unary operation is possible, otherwise it's binary operation, as because the two operands must be input to the arithmetic logic unit, and the output is the sum or the result of arithmetic logical operation. So that's why the special purpose registers among the is the accumulator, flag register, and the instruction register. So 16-bit registers are only two, that is program counter and the stack pointer, which has a specific application, specific purpose. So these are the description of the building blocks, but you must understand the functions or the operations of the each type of the registers. For example, general purpose registers B, C, D, E, H, and L are the 6-bit general purpose register can be used for as a separate 8-bit register or as 16-bit pair register pair like B, C, D, E, and HL. When used in the register pair mode, the higher order byte in the operand on the number resides in the first registers, that is in BC pair B, and the lower order byte will be associated with the second register, that is C. HL pair also functions as a data pointer or memory pointer register. I will explain what is the purpose of memory pointing or data pointer. These are also called the scratch pad register, HL pair, 16-bit register. The temporary registers are utilized for the arithmetic logical operation. Now, how the arithmetic logical operation will proceed, that needs to be understood. For example, with the help of a particular instruction in machine code, whose symbolic or grammatical name is add b, means the arithmetic group of the arithmetic group of the instruction which adds the content of the A register, which is implied. There is no A register, but B is explicitly used. So the content of the A and the B registers are summed and stores the result in the A registers. That means add B means an addition operation or arithmetic operation which performs the content to be added, stored in the A register, that is accumulator, and the B register, and the result of the operation, that is C, will be stored in the accumulator, that is A register. So that is the meaning of this add B. So there are some discrete steps of operation. So add B is a symbolic name or called the mnemonic of the instruction to be executed by the 8085 microprocessor, and ultimately it will proceed in the discrete time steps or slots. So how to represent the micro instructions, because add B is grammatically a word, but to execute, the microprocessor cannot understand this word, rather it can understand the steps of operation. So there is a method to write the micro instruction steps associated with a single instruction like add B. So we must understand step by step, not right now, how the instruction can be executed by the microprocessor. So what I was telling, that means the W and Z registers are the temporary registers. During this operation, they can be used to store the intermittent results. What is intermittent result? Intermediate results. That means, first of all, the one register content should be stored to the content of the W or Z, whatever may be. Then the another register must take place to accept the number, one number, that is A accumulator. Then it will be, that means W and the Z register, that means one of the operands will be stored to the accumulator and the other operand will be stored in either Z and W. So that's why there is a role of the temporary register, which will take part in arithmetic operations as well as the logical operation. So again, the W and Z, that is the temporary register, plays an important part in a particular type of instruction call. It will be described when when we will study the type of instruction or classification of the instruction. So call is an instruction which can be used efficiently for accessing the subroutine or subprogram. So the special purpose registers, among the special purpose register is the A register called the accumulator, and flag registers, which is very important. Flag register is also 8-bit, but it has a relative order or weightage. Like least significant bit, that is the D0 bit, signifies the carry flag. Then the next significant bit, D1, does not signify nothing, so don't care. The next significant bit, that is the D2, content of the flag register, indicates the parity flag, as symbolically denoted by P. Then auxiliary carry, then 0 flag, then sign flag. So there are 1, 2, 3, 4, 5 single bit flag status, which can result from arithmetic and the logical operations. Now, how the carry will be generated? That means generated means when the bit will be set to 1 Otherwise, normally all this flag bit will be reset to 0. That means initially, when the microprocessor is just powered on, the content of the flag register at the initial state will be all 0. But if the microprocessor performs an arithmetic or the logical operation, depending on the nature of the operand, carry flag may be set, parity flag may be set, auxiliary carry may be set, zero flag may be set, and sign flag may be set. So we will discuss under what circumstances or condition the individual flag bit will be set or reset, and that will be stored in the flag register. Under program control, with the help of the separate instruction, the programmer or the user can access the status of the flag register individually. So the description is like that. After execution of the arithmetic or logical operation, if the D7 bit results 1, we mean the sign flag is set. In a given byte, if the D7 is 1, the number will be viewed as a negative number. For example, there are signed arithmetic as well as the unsigned arithmetic in binary operations. So you require the knowledge of what is sign bit operation, sign number operation. For example, generally we are conversant about the unsigned operation. That means every binary number are treated as a positive integer. Accordingly, the summation will proceed. But if the binary number is expressed as a signed number notation, then generally the most significant bit carries the sign information. For example, if the most significant bit is to 1, the number is negative, having magnitude as well as the sign bit. If the most significant bit is reset to 0, the number is treated as a positive number. For a sign bit system. Otherwise, for an unsigned number, there is as such no sign information in the most significant bit. Now, what is the description of the zero flag, how it works, how it will be set? The zero flag says if the result of operation in ALU is 0, that means whenever the ALU holds the intermediate results, which is 0, then automatically this bit will be set to 0. The zero flag is also set if a certain register content becomes 0, following an increment of the different operations of the register. What is the meaning? That means suppose the accumulator or any registers, all the bits are set to 1. Then if this content is incremented by 1 or 1 is added, what will happen? That means an 8-bit content having all 1s will be further added by 1. Then the all bits will be 0 and carry flag will be set, because the carry will be generated from the most significant bit or addition. So the carry will be set to 1 and the zero flag will be set to 1, as upon incrementation of that particular register, the content of the register will be 0. So this is one such example. How the auxiliary carry will be set to 1, because if any number, the 4th bit is treated as an auxiliary, has a relationship with the auxiliary carry. So if the 4th bit is set to 1, automatically it will be propagated to auxiliary carry as 1. Similarly, the parity flag can be used as an odd parity or the even parity system. For example, when the microprocessor had executed some instruction, last instruction, and the accumulator contains some stream of 1. If the stream of 1 is odd, number of total ones is odd in a particular stage of accumulator, parity bit will be set to 1. Otherwise, in an even parity system, this will be set to 0. So carry flag I have described. So this is the example how the carry will be generated. For a 8-bit binary number, it is expressed in hexadecimal, that is 16 base equivalent number. 9B is a hexadecimal number, but whenever it is expressed to binary number, it is expressed in 8 bit, 1001, 1001, like that. So the carry will be generated for this addition of these two operand. And how the borrow, in the subtraction, the borrow will be generated. Whatever may be carry and borrow, it will affect the flag registered bit, that is D0 bit, called carry flag bit. So these are the significant, that these are the physical significance of the flag. Now, this is a pinout diagram. 8085 has a 40 pin. Out of 2 pins are allocated for the power supply. It is operated with a power supply voltage of maximum 8.75 DC voltage. It has a 2 power supply pin. One is called the VSS, which must be grounded to the 0 potential. Another is called the VCC, which is connected to the regulated DC power supply. Leaving these 2 pins, the 38 pins, these have a functions like that. Some of the pins we can see are symbolized as A, stands for the address lines. So A8 to A15 are the 8 number of the address lines, called the higher address lines. And 80 to 87s are the lower address line. That's why we can see not A but 80. Why? Because these lines are associated not only the address signal but also the data flow. So that's why address data. In fact, whenever the 8085 address uniquely the locations of the memory or IO, input output device, that means 8085 microprocessor, a typical microprocessor must be interfaced to form a microcomputer with some amount of the semiconductor memory, different types of the memory, as well as the input output systems called the IOs. So as a minimum subsystem, at least some amount of the IOs or the peripheral IOs and the semiconductor memory must be connected or interfaced properly with 8085. Then only it is possible that the 8085 will work successfully upon applications of the power supply, because all the instruction and the programming will be done only when some amount of the memory is allocated and the memory retains the instruction, not the microprocessor itself within its functional internal architecture. That's why we can see in the internal architecture the 8085 cannot include any memory. These are the storage element registers, not any memory. So that's why it is essentially required or needed some amount of the semiconductor memory must be interfaced with 8085 via this associated pins. So that's why these are called the address bus and these are called the address data bus. That means the nature of the signals are almost same. So this is the pinout diagram of the 8085. Some of the signals are called the bus signal, that is address bus, data bus, and some of the signals have individual entity, as they are called control and the status signals, power supply and the timing signals called the frequency, the 2 terminal X1 and X2, etc. And the description of the group of signals associated with the microprocessor are described here. We will study individually what is mean for the address data bus, what is mean for IOM bar, read bar, write bar, that is timing and the control signals. These are address latch enable ALE, what is its role? These are written here in the description column. So this is the fundamental understanding how a microprocessor chip can work. Until and unless you know the functions of each associated pin, then ultimately you cannot proceed further. So now we are in a position because I have just started the internal architecture of the microprocessor. So far, if you have any query, then you may ask right now at this junction. Otherwise, it will be very difficult because you have a limited knowledge of the digital electronics. I do not know whether you have a extensive familiarity with the digital electronics, like knowledge about combination logic circuit and the sequential logic circuit, like counter, register, etc. Please ask freely. What I have described in a simple manner, and what are the topics, what are the things you cannot understand right now. Then alternately, I will make you understand with a different manner. Please. Can you understand so far, or you find difficulties? You can follow the slides also in red colored mark, the step by step. The description has been tutored. So this is an alternative way to go through these signal lines. So this is another way. So what do you think? Do you think about the basic understanding of the internal architecture? Hello, please respond. Otherwise, how can I know that means how you have understood or not? Yes, one has responded, that means he is understanding. One of the
prerequisites
digital electronics, that means we must follow the idea of combination and the sequential logic circuit.
Flip-flops and all those.
Yes, that is the building block of making the sequential logic circuit, that is counter, registers, etc. There are different types of the register like serial in, parallel out register, parallel in, parallel out register, parallel in, serial out registers, etc. So inside the microprocessor, the registers is parallel in, parallel out registers. So you must revise yourself or very quickly, that is a sequential and the combination logic circuit. For example, the decoder is an important combination logic circuit. For microprocessor interfacing, the knowledge of the decoding or decoder is required. So this is one decoder, the combination, a typical combination logic circuit. Then decoder, encoder, there are various combination logic circuit which finds application in microprocessor subject.
So can you suggest a book for this?
Modis Mano is a textbook of the digital electronics, one of the best books. And there are so many books on the digital electronics. I suggest Modis Mano. For example, I can show right now. So this is the topic of registers. Different kind of the registers, 4 kind. How it works. You must go through this e-note from the that is the digital registers from the tutorial top point, famous site, tutorials point. So digital number systems, how the arithmetic logic unit, complement arithmetic may work in a number system. You can go through. In the binary arithmetic, what is the addition, unsigned and the signed addition? You can follow this logic. You can understand. Even without going through book, you can go through this site, tutorials point. So you can read through the Google search engine. So what are the number systems, octal, hexadecimal? These are required, knowledge is extensively required. And the rules of the binary algebra, these are frequently required. And the operations of the logic gate. Already in your first year course, you may be conversant, you have encountered. What is the role of the combination logic circuit? Like half adder, full adder. So these are the things. The parallel adder subtractor, the knowledge of which are very much required to understand how the microprocessor internally process the perform the arithmetic logic operations. So this is a functional diagram of sequential logic circuit. Sequential logic circuit includes the combination logic as well as the some storage unit called the memory element or register element. Flip-flop is one of them. SR flip-flop, JK flip-flop, master step type, T flip-flop. So these are the building block of the D flip-flop, T flip-flop. These are required to build the digital registers. So you can follow in that manner. So I have shown how to study very quickly. Or you can follow any textbook like Maurice Mano or like that. This book.
Sir, will you share these PDFs with us?
Yes, I will upload all the necessary fundamental class notes, e-notes to the Google Drive, and the link will be given to you. So I suggest to go through very quickly the very good book on digital logic system. One of this is the Maurice Mano, Digital Logic Design by Maurice Mano. Different types of the memory system. These are the lecture notes from NTPL about the microprocessor origin and the overview. Already I have discussed these things. There is a companion chart also. But these are required for information only to know, understand the origin of the microprocessor. But the amount of that is microcomputer organization, that is vast architectures are the basic things. This is a generic diagram. How the CPU, that means 8085 is a CPU name, can be interfaced with the basic functional block diagram to build the microcomputer. That's why it is called the basic components of any microcomputer. So these are also good keynotes from the NTPL. This will be supplied to you. Then the vast architecture in a better way you must go through. Otherwise, the concept will not be clear. I will proceed according, I'll follow the diagram according to this diagram. Then the interfacing with the memory will be required. That's why we require to understand the memory organization. So likewise, what is the specification of the memory, semiconductor memory? What are the architectures of any memory? Because memory somewhat is a storage element which is somewhat different from the register. Registers is also a storage element. But the volume of the storage elements available in the register is very, very small. But in case of a memory, it is large. But since the memory devices includes a large number of the registers. So this is the difference. So we will study these things. But we have just started about the internal architecture of the typical 8085 microprocessor. The recommended textbook is Ramesh Gaonkar. Ramesh Gaonkar book is also available in a different way in PDF like this. But in the textbook, the format is different. It is not available right now. Initially, it was available. So you can study one textbook like Ramesh Gaonkar. What I have started just now. So I explain how you study these subjects and what are the prerequisite knowledge. I will upload all the class notes and the recommended textbooks and the practice tutorials, etc.